split applications. So, is this? That's now not working. Okay, so what does debugging actually mean? So I've got the Wikipedia definition up there, but in all kind of axes of this definition, there's a certain amount of flex. So be it in what does a defect mean? Does it mean your program has crashed? Does it mean it's giving the wrong results? Does it mean it's performing poorly? There are many ways to debug. So you might want to do step-by-step debugging. You might want to do, if it's crashed, you want to look at it post-mortem. Or you might want to do something live. And again, different kinds of programs as well, be it a server or a command that you just run once. So what is this talk about? Because that's quite a wealth of options. So this talk will do a census of existing tools for doing debugging, and then present a vision for how we believe that debugging can move forward and become better. And the focus will be on distributed programs, so with many cooperating components, potential on different machines, and live debugging, so issues in running systems. And there's an interesting, if you've heard of Dapper before, which I'll come to later in the presentation, there's a nice quote from there where they say, Dapper is useful for some but not all firefighting tasks. Firefighting here refers to activities performed on behalf of a distributed system in peril. So that's the kind of debugging that I'm going to be focused on in this talk. If you are interested in step debugging, so as classically implemented by GDB and RR, then this may not be the talk for you. You may be more interested in looking into total view and DDT, which I understand are debuggers often used in the MPI world for debugging parallel applications. Also not going to particularly focus on post-mortem debugging, but some relevant tools will be mentioned, so may still be of interest. Disclaimers. I've not used all of the tools in this presentation in anger, so if you have questions, you're welcome to ask, but I might say I don't know. And I don't claim that this list of debugging tools is exhaustive, and if you have opinions or thoughts on things that I've missed out, I'd love to hear about it afterwards. So, what's the first port of call when your distributed system is in peril? So there's a great post by a Netflix technology blog post on what to do in the first minute when you log onto a server that is having problems. And this covers things like running dmessage to see if the kernel's logging out any issues or similar things like that. And overall node performance is a reasonably good informative first step to kind of figure out what's going on. Is there even a problem that I should be worried about? And the way that you do this is with Linux tools. So hands up if you've seen a version of this diagram before. Okay, so about a few people, about 10. And hands up if you've used a tool on here like top, strace, VMstat. Okay, so most of the people in the room. So I'm personally quite partial to strace. I haven't touched some of these. I'll mention later where you can get this diagram because it's quite useful. But if you look at what you're actually trying to do here, if you run, say, VMstat, humans don't derive meaning from a bunch of numbers. We interpret the numbers, we understand the implications, what it means for our application, and from that we can get actionable information. So understanding what's our next step in figuring out what's wrong with the system. So in this particular case, I've copied and pasted an example from the Netflix blog around usage of VMstat. So the first column, R, is the number of processes waiting for the CPU. And this can be a better representation than load average because it doesn't include I/O. And if that number is higher than the number of CPUs you have, your node's overloaded. But other than that, what do you do next? So potentially, we can use something like flame graphs. So hands up if you've used a flame graph before. Okay, about 2/3 of the room. And these are extremely useful. So this flame graph in particular is a snapshot taken from something that we did internally. And it shows stack traces from a number of samples taken of the application, typically with something like perf. And so you can have a look at this. And if I were to look at this and say, well, I need to figure out why it's running slowly, I might look at the right-hand side and go, well, there's a lot of idle CPU time. Or I might want to dig into why is this get dfire2 value taking so long? And if this were a single-threaded program, the flame graph would be highly actionable. So I would know exactly what do I want to dig into next. But unfortunately, the previous flame graph is of a distributed system, which is of one manager driving computation of a number of workers and assorted other connected components. And it's just an average. So this is just an average over all of those components. So a quick interlude to give context around the motivation here. So this is the one of the applications that Aidan builds, which is a distributed simulation engine. On the left-hand side, out the left, is the manager, which drives computation of a number of workers connected to each other, which hand entities between these different workers, and those then get replicated to the clients. And this is an oversimplification. It's not actually a grid, it's a bit more flexible than that. These workers can go down and be spun up dynamically, but it gets the thrust across. Workers, in this case, correspond to physical CPU cores, maybe on the same node, maybe on a different node. Now, the previous flame graph was from, it's not just useful for MMO backends, so the flame graph I showed you just before was from a simulation that we were doing with the Francis Crick Institute for protein modeling. And there's no Docker or Kubernetes here. We have our own distributed process model to make those things not relevant. But because this is a distributed system running across potentially many nodes, it means that the flame graph in itself is not very actionable. It's informative. It might kind of give us a rough idea of are things as we expect, assuming that we have an intuition about what it should look like beforehand. But how can we make things more actionable? How can we find a better way to look at the representation and go, I understand what I need to look into next. So, next on the list of tools is state maps. So, hands up if you've heard of or seen state maps before. Okay, nobody. So, state maps are a tool, I don't know when they were first created, but I've seen them come up most recently in a presentation from Brian Cantrill, who worked at Joyent. And this is quite a nice way of representing the different states of the system. So it's a general tool where different states of the system are represented with different colors. In this particular case, it's the darker reds, and this is just an example taken from one of the presentations on state maps, In this case, the darker reds represent more I/O activity. And so you can see that there are gaps in this I/O activity across 8 different nodes. In this particular example, each row is a state map in itself, and they've been stacked on top of each other. And within each of these rows are sub-rows for each thread or process. So I might look at this and go, well, I don't understand why there's uneven I/O activity. I don't understand why there are these pauses. I need to look into it. And I highly recommend watching the presentation that Brian Cantrell did on state maps, where he describes going through an investigation of why a database is running slowly. And I won't spoil the end result for you. But as I said, this is general. So these states can be whether you're waiting on I/O, whether you're on CPU, whether you're fully idle, and so on. And this is kind of useful, right? Using this on a distributed program, running across a number of different machines, a human can spot patterns. In this case, it's fairly clear to see that there are periods of I/O idleness all happening at the same time across many machines. That's kind of useful. You can see what else was going on when the system slowed down. In the case of the worked example that Brian does on Postgres, you can see the auto vacuumer, you can see different threads within the database. But this potentially gets a bit harder when you're working with massively distributed applications. So if you imagine, rather than 8, you have 100 of these stacked state maps. How are you going to spot the patterns without a really big ruler? It gets a bit harder. And additionally, distributed systems are a multiplicity of cooperating components. They communicate with each other, potentially to different machines. There's no explicit representation of that here. There's something implicit where in the Postgres talk you can see that computation halts until a particular event happens, and then everything continues, and you can kind of go, I'm inferring that there's something funny going on here that I need to investigate. But there's nothing explicit to be representative of the structure. So, the next kind of idea on this road is system graphs. So, there are 3 different ones that I put up here. This is not a new idea, it's been done a number of times. So on the top left is something that I came across relatively recently, Constellate. It's not a live system viewer, it's actually just for designing a template for use in Kubernetes. Observer on the top right is built into Erlang. So you can start that in Erlang, monitor a running Erlang system, and this particular tab in the top right is showing the supervision tree of an Erlang application. The bottom one is an internal tool at Aidan that we've creatively named NetVis, Network Visualizer, which shows the different processes in Ether and how they're connected and how they communicate with each other. You can click and hover over different nodes to get detailed information about their bandwidth usage, what they're connected to, and so on. Out of curiosity, who's used or heard of Observer in Erlang before? Okay, so about 7 people or so. So this is interesting because it's giving us a better intuition. It's closer mapped how we think about our distributed system. It shows the connections, it shows how they're interacting with each other. But we're still relying on the human to figure out, well, this worker, I need to click around the workers, see if there's anything overloaded in order to make it actionable, in order to know what to do next. So it's a better representation, but maybe it doesn't move the needle so much on actually getting us to a place where we can take our distributed system in peril and go, right, this is how I'm going to fix it. So if we look at how distributed systems are designed, they're often in terms of groups of components and then how these groups of components actually interact with each other. Why are we thinking about these applications on their lowest level in terms of threads, in terms of Linux processes, in terms of nodes, rather than conceptually at their architectural level, and how data flows through them? So, tracing is I wouldn't say it's relatively new, but it's certainly entering mainstream consciousness in terms of its usage. So top left is a picture from the Google Dapper paper, which was, as far as I am aware, the first in-depth exploration in how you can use tracing in a system. Please correct me if you're aware of something else. Jaeger is to the top right, is open source, and Zipkin is at the bottom. Behind the scenes, there's another piece to these two open source ones, open tracing. So hands up if you've heard of any of these. Okay, about half the room. Hands up if you've used them. Okay, about the same number. And these are extremely powerful tools. Because they are very actionable and representative of your application. You're actually following a request as it comes through your system. So in the original Dapper paper in 2010, I think it was, there's this notion of spans where you, within a particular region of code, you follow what a request is doing, and this may follow a request across to another machine to see how that affects the processing, and so you can get a full trace, per the name, of what's actually been happening in the history. So if you look at the top right on the bottom here, this is an example from Jaeger of this. So highly actionable, representative of your application, requires you to add annotations to and change your application to opt into this kind of power. It's potentially not that informative of whether you have a problem or not, unless you're already asking the right questions. So it would be unusual to jump in and go, right, I want to see the trace of request ID X, or I want to see the latency of the last n requests, and that tells you if you've got a problem with your application. Typically, it would be driven by another observation where you kind of follow the breadcrumbs and then you end up in tracing. So Dapper style tracing is static. You actually have to write it in your application, and it will follow through what you're as you've programmed it, which makes it very application specific and informative for your particular use case. By contrast, who's heard of tracing in Erlang or sectrace? So 3 people or so. Tracing in Erlang is dynamic, which may make sense due to the nature of Erlang. and typically is a little different to Dapper style tracing in that it will refer to emitting messages rather than following a request through the system. That said, there is the sec_trace module, which allows you to follow the effect of messages through the system, which, while potentially not as application specific and targeted as Dapper style, will provide similar functionality. Now, all of these views are valid. All of them are useful for different things. I've kind of touched on Linux tools, I've touched on flame graphs, state maps, system graphs or network graphs, and tracing of different kinds. And each of them have their own limitations. So we want something that's representative, that is, matches our intuitions about the system. Informative is tells us if there's actually something going wrong, and actionable tells us what we need to do next. So what's the answer? And to be clear, there is going to be no tool that you can download at the end of this talk. This is an exploration of what we're looking into and what we're building at the moment. And our vision for this is debugging lenses. And this does not refer to Haskell lens. This refers to if you have an array of magnifying glasses, or as pictured on the screen, a watchmaker's set of spectacles that you can swap the lenses in and out of, to be able to look at your system in different ways. And the key pieces of this that we believe are important and are potentially missing in the context of what we're trying to pursue are dynamically addable tracing and first-class distributed system support, as well as swappable visualizations. We've just established that all of these previous ways of looking at the system are valid. So why should we lock ourselves into just doing tracing or just having a state map? The visualizations and representations need to be application focused as well, because otherwise you're back to the days of Linux tools where you're running VMstat and you've got CPU usage and you don't really know how that relates to your application. And so because they're customizable, because they're buildable by the user, because they're dynamic, they can be representative, informative, and actionable. These are arbitrary words I've chosen to describe these concepts as appropriate for the use case. So let's take a look at a block diagram of what this might look like. So this is an example high-level kind of lens or dashboard for Ether. We have some actual prototypes of this, but the important aspect is the representation. This could be hosted in Grafana, this could be custom HTML, it doesn't really matter. The important side of it is what it's actually showing you. So in this particular case, we were talking about Ether as a game backend. For MMO games, it partitions the space based on the resource usage. So we care about player experience. And on that front, there are three key pieces that we're interested in. Time to get events from the player into the system, the time it takes for the simulation to run, and whether we're in the budget for our tick. So if you're running at 15 ticks a second on the server side, then you have a certain budget in which to do all your simulation, and time to get state out of the system to the user. Additionally of interest is how much bandwidth you're using, because if you're saturating the user's broadband, they may not be best pleased. And this is then the high-level dashboard that you'd be looking at. So at the top is the simulation performance itself. In this particular case, it's truly awful simulation performance. You can see that, I think these are, so the tick budget is about 66 milliseconds for 15 ticks a second, and these were spikes of about 5 seconds. So that's not that great. We can instantly see that there's something that we need to look at in terms of the simulation performance. On the left and on the right, it talks about data coming in and out of the system. And so there are two deliberate pieces to note about this. First is that it's a rather graphical layout of the system. It matches the intuition. There are clients in one location on the dashboard, and there's the simulation itself separated physically on the screen. And so it's a closer mapping than if we just have a number of tables with numbers in them. Another thing to note is the max. So this is just an example of how you can easily make something more actionable. So if you have information about the mean of a system, then okay, that's great, you know roughly how it's performing. But you don't have any information about the long tail, about the worst experience. If you have a max, if you take the worst case, that's an instantly actionable thing. If it's completely unacceptable, you can instantly go, all right, player 2 is having a terrible time with bandwidth. They must be maxing out their bandwidth to send all of this data into the simulation. We need to figure out what's going on. You can instantly start drilling down into that particular player. So this is kind of the top-level performance lens that you might imagine. Let's look at another one. Cost. So somewhat controversially, games companies do want to make money. And part of making money is not spending all of your money on infrastructure. Is this debugging? Well, for the person who holds the purse strings, if suddenly you're spending thousands of dollars an hour, that may well be considered a bug. So this is a view in this of how you might progress through the lenses. So on the left-hand side is the top-level cost lens, where you've got your total cost, your cost per player, etc., and your breakdown. So ultimately, in the case of Ether, cost comes from two places. Machines that you're running and bandwidth out. That's it. So then you might want to have very quickly a machine analysis, because if your cost is mainly in machines, then typically that will be because, given that Ether is a automatically scaling system, this will be because there's something CPU saturated and so it's expanded out, or something memory saturated. And so if you look, now if it's neither of those, then there's something else going on. Maybe network traffic has bottlenecked you or something like that. And so you might go the route of, on the top, of going into a state map. You need to get all the workers stacked on a state map and look at what's going on. In the mid case, you want to look into actually your bandwidth breakdown. So how much bandwidth are we putting out to the worst case player? How much bandwidth are we putting out on average? For that worst case player, what's actually in the packets that we're sending to them? And this is something that games companies are somewhat obsessive about, trying to reduce bandwidth to improve player experience. Finally, if you wanted to look at worker CPU usage, so generally that will be in your simulation step, you might want to look into, well, we've got non-player character enemies are taking 1% of the CPU time, missile targeting is taking 50%, and physics is taking 5%. So unfortunately the slides changed, but in this case, we can see that worker CPU usage, we've got a max of 100. Machine A, for some reason, is completely maxed out. Maybe we want to look into that. The feature CPU usage, well, 50% is on missile targeting. Why is it taking so much time to do pathfinding? This seems completely unreasonable. And so, using this, you can see the way that if you build up a corpus of lenses, a corpus of different ways of looking at your system, you can quickly narrow down the problem and get closer to actually being able to fix it. That is, getting actionable information out. One thing that I touched on a little bit earlier was around dynamic tracing. So that is the Dapper style, you write the code before you deploy your application, versus Erlang, where you can do it on the fly. The vast majority of things, of measurements on this slide, can be done dynamically. And this is even for native code. So all of Ether is written in C++. Generally, this means that it can be a little bit tricky to instrument code after the fact. But using, so who's heard of eBPF? Okay, a couple of people. So this is tracing functionality tracing functionality built into Linux that you can use to instrument applications that are running. And we're still exploring the performance impact of this, but there is opportunity to, when you're debugging an application, express that, hey, I don't know why this function's being called n,000 times. Let's actually dynamically add to my running system some instrumentation that tells me who's calling this function and with what arguments. Why is this happening? And so you can make your firefighting or debugging of the live system more of a conversation, which is, in the end, what you want to tend towards, because it's about, debugging is about asking the right questions, getting an answer, and asking more specific questions until you've actually found the cause of the issue. So, I've mentioned a number of different things in here. So these are, hopefully these are visible, yes. So throughout this presentation, I've talked through step debugging, Linux debugging, this blog post, as well as, and this link to Brendan Gregg's website is where you can get the diagrams of the Linux tools, which are great to stick above your monitor. Flame graphs, and also a tool that Netflix has released along the same lines. State map related things. So there's state maps themselves from Joyent and Brian Cantrell, and honorable mentions to other tools, so that are not focused on distributed applications, more on single node applications. Tracy and telemetry from Rad Game Tools. So network visualization, mentioned Constellate, which doesn't seem particularly active, but exists, and Erlang Observer. Tracing is a massive ecosystem that would be a talk in its own right, so I gave it very brief coverage here. So open tracing is, I understand, turning into open telemetry. And then there's the Erlang interfaces on top of the core Erlang tooling. So Redbug and Early Burly, both of which both of which provide a more human interface to these low-level systems. And finally, if you are interested in network profiling and network debugging, which is something that I've become very immersed in since working a little bit with the games industry, the I Shot You First, Networking the Gameplay of Halo Reach, is an excellent talk that goes into how they built a bandwidth profiler within their game itself in order to figure out, well, what is taking up all of my bandwidth and how can we improve it? And it also talks about a number of techniques for reducing bandwidth that may only be relevant for games. If you want to see the profiler, skip to, well, 109.15. And that's all I have. Any questions? Thank you very much.
We now have a short break and we'll be back in half an hour.